Hi, welcome back to es346 Basic Thermodynamics. This is module 7.2, Entropy Property Relations. The sections in the textbook are 7.3 to 7.5. Here are the three learning outcomes. At the end, you'll be able to quantify entropy change for a mixture, you'll be able to calculate the entropy change in a process using other properties, and you'll be able to determine property changes during an isentropic process. So I want to look at the TS diagram that we've mentioned briefly before. And since entropy is a property, we can go ahead and use that in the state postulate and draw a two-dimensional diagram for which all states of matter are going to appear on. And we'll go ahead and look at a phase change material in this example. So, for example, water. And then the way the TS diagram looks like, it's sort of similar to PV where you kind of have this hill region. It's a little bit sloped a little differently, but generally it's the same sort of shape. We're up at the very top. This is the critical point, and it separates liquids and vapors. This over here is my saturated liquid line. On the right-hand side is my saturated vapor line. There are compressed liquids over on the left, and there are superheated vapors on the right. Ideal gas land is sort of in this range out here in the far right. Values of entropy, which we use the symbol S for, along that line right there, those will be S sub F values. So we use subscript F like we do with internal energy, enthalpy, and volume. And those along this line right here will be S sub G values. And if I want to go ahead and determine what the quality is for something underneath here, so this region in here is the mixture region, X is going to be defined similar to what we did with internal energy and entropy. S over SF, SG minus SF. Or if I wanted to solve for the entropy of a mixture, S, by rearranging this equation, is SF plus X, SFG. So we realize that entropy S is a lot like internal energy, enthalpy, and volume. So we'll go ahead and add S to that list of materials. Let's go ahead and do an example here. I have 2 kilograms of water. It's initially a mixture. Its initial pressure is 100 kilopascals and a quality 0.75. And it's heated until it's a saturated vapor in a constant volume tank. So I'm adding heat here. In the end, it's going to be saturated vapor. And we want to know what is the change in entropy of this. So, well, change in entropy. And one thing we saw we could do before was we just needed to integrate del Q over T, assuming that you knew what those values were. And that's not very convenient for this problem. So if we think of what a TS diagram looks like in this problem, I'm starting off with a mixture and somewhere underneath, and if I go ahead and add energy in a constant volume, the temperature is going to go up, and at some point I'm going to have an increase in entropy, and that would be 0.2. So I realize that temperature is changing all along there, and so doing this integral would be somewhat difficult. So this is not the preferred way to do it. But since entropy is a property, all we need to know is 0.1 and 0.2, and then I can calculate delta S as M S2 minus S1. So I just need to know what the entropy is at those 2 points. And I've got 2 intensive variables at the initial state. I've got a pressure and quality. So I can go ahead and find out what S1 is. S1 is SF plus X, SFG. And so I'm going to go ahead and pull values off the table. I'm going to go to the pressure table, and on the far right-hand side are entropy values, and so this is 1.3028, that's the SF value, plus 0.75, and SFG is 6.0562, and there's my S1 value at 2.8168 units of kilojoules per kilogram Kelvin. All right. So now I need to find out what is S2, and what do I know at the final state is that it's a saturated vapor, but it's in a constant volume, so I also know that the volume didn't change. So my mixture, my pair of intensive variables now is going to be V and X. I know both of those. So let's go ahead and find out what V1 is a similar way. I've got VF plus X VFG. So same line on the table. I'm going to go ahead and pull those values of V. And I'm going to just skip the steps here a little bit in terms of space. And this will be 0.434 meters cubed per kilogram. Constant volume, so that's also the V2. And we know it's a saturated vapor, so that's going to be a value of V sub X. So what I need to do now is just go ahead and find out where is a VF value with this value of the volume, and then read off the corresponding entropy to find out what is S2. So let's go ahead and look at the tables for that. So here I've got an excerpt from table A5, and here are my VG values, and I was looking for 0.434, so it's going to occur somewhere between that, so somewhere between 400 and 450 kilopascals. And so I've got a saturated vapor for entropy. There's my SG values, and it's going to be something between 6.8955 and 6.8561. So let's go ahead and determine that by interpolation. So we have S2 minus, and so I'm going to go ahead and use the top line there. So 6.8955 over 6.8561 minus 6.8955 is equal to, and then I'm going to use the volume, which is 0.464 minus, and I was doing the top outline there, so this would be 0.46242, so 0.41392 minus 0.46242. To go ahead and find out what is S2, and S2 is 6.8724. All right, so there's my value of S2. Let's go ahead and finish this. I'll go back to the previous slide here, find out what delta S is. It's going to be my mass of 2 kilograms, and then my two values of S. So S2 was 6.8724 minus S1, which is 2.8168, and that comes out to be, the arithmetic on that is 8.111 kilojoules per Kelvin. That is the change in entropy during that deification process. Let's talk a little bit about isentropic processes. And isentropic means that delta S is 0. There's no change in entropy. And so imagine that I had a compressor here. And so coming in at some pressure of P1, T1, it could be coming out at a P2 and a T2. If the entropy doesn't change, that says S1 over here, or S2 would just be equal to S1. So that means that it's isentropic. There's no change in entropy. And there's a couple ways that you can have an isentropic process. One is it can be completely reversible, which means there's not going to be any heat transfer. So, for example, Q could be equal to 0, and it could be reversible, and meaning there's no friction. Therefore, delta S is 0. Right? Because I got it reversible, and I'm not allowing any heat transfer to occur. But that's not the only way to have it. I could have friction in here and some heat transfer, some heat to leave, and essentially enough heat from that's being generated by the friction. Go back to a previous module, we had the piston cylinders that were sort of rusty. So you go ahead and lose the heat at the rate that you're generating in there. So that means I can have Q not being equal to 0, right? Some of it's being leaving, but it's irreversible, and those are going to balance out such that delta S could be 0. You can have two different types of isentropic processes. Q equals 0 reversible, Q not 0 and irreversible. But they need to be one of those two cases. Now, if you look at this, you can turn some stuff around and realize that, well, if delta S is equal to 0, and we know that it is reversible, therefore we know Q has to be equal to 0. You also realize that if delta S is 0 and it was irreversible, Q cannot be equal to 0. That comes from just rearranging these necessary but not sufficient conditions. Let's go ahead and do an example here. We can find entropy as a property from other properties. And what I have is I have steam in this turbine here. Water vapor is being expanded. It's happened isentropically. And I want to know what's the outlet temperature. So what is the temperature down there? Right? Well, if it's isentropic, I've got an S1, and I'm going to have an S2, which is equal to S1. So the entropy doesn't change as I move through. And I've got these two intensive variables, so I can go ahead and find out what S1 is from that. So what I'm going to do is go to the superheated tables at 15 megapascals and 600 degrees and just read off what the entropy is. And that value of S1 off the superheated tables is 6.6796 in there, kilojoules per kilogram. Right? And then I want to go ahead and tell, I know that that is also equal to S2. And so if I want to go ahead and find out, well, what is the temperature of S2, oops, I'm going to need to go and look at what is the value of S at 200 kPa. And well, I realize that S sub G at 200 kPa is 7.172, and that's kilojoules per kilogram. Oops, per Kelvin, that's per Kelvin. So this is S sub G at 200 kPa. Right? So this value is less than this, so that means that I must have a mixture, and I can verify that if I look at my SF value at 200 kPa. So again, I'm using these outlet conditions down here. That's 1.5302 kilojoules per kilogram Kelvin. So my value of S2 is between those two, which means I have a mixture down here, and that means that T is going to be equal to Tsat at 200 kPa, and that's 120.2 degrees Celsius. Let's look a little bit about Carnot cycle entropies. And first I'll go ahead and look at this in the vapor phase. And remember the Carnot cycle had 4 steps, 2 isentropic and 2 isothermal steps. So I'm going to go ahead and draw a couple, just some isotherms on here. And I lost my pen again. Oh, there we go. Okay. Draw a couple isotherms on here. And so if I look at the Carnot cycle, I've got an isothermal step followed by an isentropic step. So this would be TH, this would be TL, and then another isentropic step or isothermal step followed by an isentropic step. And so that's what the Carnot cycle would look like on a TS diagram. Right? Now we can look at this in the vapor-liquid region, or what I call a Rankine cycle. So now I've got a TS diagram, but instead of ideal gas land, I have sort of this hill. And so if I want to have an isothermal step, it's going to have to be across the mixture region that way. And then if I'm going to go ahead and have an isentropic step, it's going to drop straight down, straight over, and that's straight up. So this right over here is the Carnot cycle in the vapor-liquid region.